The branch and bound technique allows to solve the TSP instances exactly in practice. That is, the branch and bound algorithm is guaranteed to output the best, that is, optimal solution. The only issue is that it is not guaranteed to have low running time. That is, on some instances it is quick, on some instances it is slow. Its main idea is the following. Assume that we were just enumerating all possible cycles or all possible permutations. How would we do this? So we start with some node. Then we know that from this node we can go to either this node or that node or that node. So n-1 other nodes. From each of these nodes we can go to either this one or this one or this one. So we construct like recursively these tree of all permutations. At the same time, for some branches of the tree, we can cut them somewhere in the middle just because we already know that this branch or this current subpath cannot be extended to an optimal solution. And this is best illustrated with an example. So just consider this small graph with 4 nodes, and this is how the whole tree of all permutation looks like. So from the node, we start with node 1. Okay, from 1 we can go to either 2, 3 or 4. Okay, from the node 2 we can go either to 3 or 4, just because we do not go to 1 because 1 is already visited. Similarly, from node 3 we can go either to 2 or to 4. Okay, from the node 4 we can go to either 2 or 3. Again, because 1 is already visited. Okay, then from 3 we have already no choice, we need to go to 4 and then to go back to 1 and so on. So the leaves of this tree correspond to all possible permutations. And actually from all possible permutations starting with 1, and you see that 7 is the best length of a cycle. So the best cycle in this case is, let me draw it on our toy example, is going from 1 to 2, from 2 to 4, from 4 to 3, and from 3 to 1, right? Which gives us a cycle of length 7. And we see that there is another cycle of length 7, and essentially this is the same cycle but traversed in another direction. So since here we have a non-directed graph, so every cycle will appear twice in our recursive tree. Okay, and now comes the idea of pruning the search tree, and this is actually the essence of the branch and bound technique. Let's do the following. Let's construct this recursion tree just node by node. Okay, so we start at node number 0. So when we just stay at node number 1, I'm sorry, when we just stay at node number 1, so the length of the current subpath is equal to 0 because we haven't yet traversed any edge. Then from node number 1 we can go to node number 2, and at this point the length of the current path is equal to 1 because we already traversed this edge of length 1. Okay, from 2 we go to 3, and the length of the current path is equal to 6. So this is just because this is just 1 plus 5. So we update the length of the current subpath. Finally, from 3, the only available vertex, the only available node is 4, so we go to 4 and then we return back to 1, and then we save the information that we already see in the cycle, a cycle of length 19. Okay, so we save it in a variable called something like best so far. So this is a very useful information, and we will use it in order to cut some of the branches in our tree. Now let's get back to the nearest node where there was some choice, and this is this node actually, because from 2 we might as well go to the node 4. So let's try to go to the node 4. So this gives us a subpath. So this subpath in the initial graph, it corresponds to this one, and it has length 3. Okay, from 4 we go to 3, and then we have no choice again, so we return back to the node 1, and now we see that this leads us to a better cycle of length 7, and we save it in our variable best so far. Okay, this actually means that if we are extending some path and we see that its length is already greater than 7, then there is just no sense in extending it further. right? Because we already have a cycle of length 7 and we are interested in a shorter such cycle. So let's get back to where we started and let's try from the first node to go to the third node. Okay, we go from 1 to 3, then we go from 3 to 2, then from 2 to 4, and now we see that this path is already too long. So there is no sense in extending it, but actually we do not save anything at this point because, well, we already traversed all the nodes. But then let's consider what happens in another branch. Well, in another branch we again find this cycle of length 7, but then in the final branch, if from the first node we go to the fourth node, then we see that in this case there is no sense of like extending further this subtree, because already going from 0 to the node 4 gives us a path which is longer than the best cycle that we've seen so far, right? So definitely if we use this very heavy edge, we are not going to extend it to a cycle which is going to be shorter than 7, right? So using this very simple idea, we were able to cut some of the branches. So for this toy example, the savings are modest, of course, but when the graph is larger and there is a larger deviation in the edge weights, the savings might be very dramatic. Okay, so once again, what we used to lower bound the length of the cycles that we can get in the current branch is almost something trivial, right? So we used the following fact: if the length of the current subpath is too long, then it is definitely cannot be extended to something which is better than the optimal one, right? If it is already longer than optimal, then by adding some edges would not make it less than optimal, right? And this is basically the whole approach is used in some of the very efficient state-of-the-art TSP solvers. However, the heuristics or the methods for lower bounding all the extensions of the current path used in these solvers are much trickier. Let me just mention two of such methods which are still simple enough, and in practice much more complicated things are used. So imagine that we would like to, we have a graph and we would like to compute quickly some lower bound on the length of the optimal TSP cycle in this graph. So the first approach tells us that we can compute the following quantity. So for every node in this graph, we take two edges, two incident edges. Assume for simplicity that the graph is undirected. Then we just take two edges of minimum weight that are adjacent to this node. So we compute the sum of all such edges for all the nodes and we take 1/2 of them. So I claim that this gives us a lower bound for the optimum TSP cycle. So why is that? Well, just because in a cycle, in a TSP cycle, for every node, we have to use two adjacent edges. For example, for this node, we use this edge and this edge. Okay, right? So for every node, we need to use two adjacent edges, and the sum of the weights of these two adjacent edges are definitely at least the sum of the of two minimum weight edges adjacent to this node, right? So this is a clear lower bound. So the only thing that should be clarified is that why we have this 1/2 here. This is just because when computing all these minimum edges for all the nodes, some of the edges can be computed twice. For example, this node might be the minimum adjacent edge to this node and to that node, right? And since we computed it twice, to make this lower bound to work, we need to take the half of all of the sum of all these edges. So this is a quantity that can be computed very quickly, very efficiently, and this already gives us a lower bound. Okay, so if we see that this lower bound is already greater than the best solution that we've seen so far, then we stop immediately and we cut the current branch. Okay, so another way of lower bounding the cycle, the optimum cycle, is the following. So assume that we have a graph. and we construct an the minimum spanning tree in this graph, and assume that the graph is undirected also. Then what I claim is that the weight of this minimum spanning tree is at most the weight of the traveling salesman person cycle. Why is that? Well, again, let's consider an optimal traveling salesman person cycle. So this is, let me just denote its weight just by TSP. Now let me do the following. Let me just remove some edge. Okay? Then what we know is that since all the edge weights are non-negative, we know that what is left has weight smaller than the traveling salesman person cycle. And also, as you can see from this picture, what we get is some spanning tree. Okay, so this is just a path, but this is a special case of a tree. It spans all the nodes, and it has n-1 edges. So what we know is that TSP is at least the weight of this particular tree, right? And this tree, this is a tree. This is a spanning tree. Okay, let me write it. Spanning tree. And the weight of this spanning tree is definitely at least the weight of the minimum spanning tree, because the weight of the minimum spanning tree is the smallest one, right? And this finally proves that the weight of the optimal TSP cycle is at least the weight of the minimum spanning tree. And as you probably remember, the minimum spanning tree can be computed very efficiently, almost in linear time. So it is quite easy to compute minimum spanning tree, I mean, even for graphs with thousands of edges. Okay, so it can be computed just in a greedy fashion. We keep taking edges one by one, starting from the lightest one. Okay. Okay, now let me summarize. So the branch and bound technique. So it consists actually of two methods. The first one is how we enumerate all the nodes all the nodes that are going to be visited after the current one. In our example, we consider it just some random order. When implementing this idea, it makes sense to stick to some particular heuristic. For example, a reasonable choice of like going to the next node is to go to the nearest next node. So if we went from 1 to 2, and then we are choosing the next node to go, then it makes sense to start probably not with the node number 3, but with the node number 5, if the edge from 2 to 5 is shorter than the edge from 2 to 3. So it makes sense to enumerate nodes to visit the next nodes in order of the increasing distance from the current node. Okay. The next heuristic used inside a branch and bound algorithm is how we lower bound the cycle in the remaining graph. Okay, so we've used, in our toy example, we used a very simple one, and then we've discussed two slightly more complicated ways of measuring. From this way of measuring, we need the following two things. First, it is efficiently computable. Okay, we would like to compute this lower bound very quickly, and on the other hand, it should be a lower bound. It should be a quantity such that the traveling salesman person cycle is at least this quantity. Okay, so as we've discussed already, this is guaranteed to find an optimal solution, because we're essentially enumerating all possible cycles, and we cut only the branches where we're absolutely sure that there is no optimal cycle, because the cycles that we're going to find in this branch is definitely longer than some cycles that we've seen before. Okay, so the running time of this idea actually depends on the instance itself and the two heuristic used. So the smarter are the heuristic, the better is the running time usually. At the same time, if the heuristic works, if the heuristic of lower bounding, for example, is too slow, this can be a trade-off. So sometimes the heuristic gives a good lower bound, but it works, but it is too slow, for example. So there is some trade-off. Okay, so finally let me mention this is exactly the idea that is used in modern TCP solvers that are actually able to solve instances of the traveling salesman person problem consisting of thousands of nodes.